Good morning. This lecture will begin a series of lectures dealing with forces. There are a lot of forces in nature that we deal with and that we have to be able to calculate. Those forces include gravity, which most of us know about, friction, and there are some other forces. And so in this section, we will separate out each lecture. We'll study gravity, we'll study Newton's second law and friction, torque, which is actually a force applied at a distance, and something called static equilibrium. So we will actually have 5 different lectures on topics having to do with forces. Later on, we'll then go and study centripetal force and circular motion. To begin with, let's talk about gravity. Gravity is something that a lot of people think Newton is responsible for. Gravity's been around a long time, long before Newton. Gravity is a force. It's a force of attraction. It's a force of attraction between masses. And so if we were to put a simple definition, it would be a force of attraction between masses. Now, most people think, well, it's the Earth pulling on things. Well, the moon is pulling on things also, and so is the sun. But it's just not large heavenly objects that are pulling on things. Even small masses are pulling on each other. So a book is pulling on a pencil. Well, we don't see that very often, or we can't recognize that. And so the force of gravity must depend upon something, and probably depending upon the mass. And so we say that the force of gravity depends upon, so the force depends upon several things. One, the mass of the object. But most people don't understand, it's also the mass of the object being pulled, the mass of the other object. You see, the Earth can pull down on a person, but it's not only the mass of the Earth, but it's the mass of the person that makes a difference. The bigger the planet, the bigger the person, that force increases. One thing that's also there is the distance between the masses. The further the distance is, the less the force becomes. And so as one increases a distance from the planet Earth, the force of gravity on that person becomes less and less. So the distance will have something to do with that. Therefore, we can say that the force of gravity is somehow related to the mass of the two objects. We'll call it mass 1 and mass 2, and the distance between them. Now, the reason the distance is at the bottom of that proportionality is because as a number on the denominator gets larger, the amount of force would get smaller. And so as the mass increases, greater force. But as the distance increases, less force. Well, it just so happens that that's not an equation. In order to turn that into an equation, we need to add a constant. And so the force of gravity formula is said to be this. It's a constant g, called the gravitational constant, which we'll speak about in just a minute, times mass 1 times mass 2, whatever those two masses be, divided by the distance. Now, after doing a lot of experimentation, we found out that this distance, the actual formula is distance squared. And that was done empirically. Empirical means it's done through experimentation. So what happens is, if you double the distance you are from, say, the planet Earth, one would expect that the force of gravity would be half. However, we find out it's a quarter as much. If you triple your distance, one would expect that the force of gravity would be 1/3 as much, but it's really 1/9. It's the square of that. And that work was done by a man by the name of Henry Cavendish. And Henry Cavendish did this little experiment where let's see if we can understand this. He had suspended from a wire a, a pole that had two small masses on it. And on that wire was a mirror. He brought larger masses near the smaller ones, and the smaller masses were tugged toward the larger masses. It turned that wire, turning the mirror, and although you can't see the wire turn very much, if the mirror turns just a little bit, any bit of light hitting the mirror will move. And there would have been a scale down here that he could have seen that move along. And he could actually measure small amounts of gravity. I think I have another picture of that to show you. This can be done in a lab setting. We have, if you look, we have a fiber with a mirror attached. And then we have larger spheres and smaller spheres. And the smaller spheres are the ones that are attached to the little fiber, and which is attached to the mirror. Okay, it's a very sensitive experiment. But Henry Cavendish had done this work. And when he did this work, he was able to determine what this constant G is. And this constant G is a universal constant. It's called the universal gravitational constant. And it's a number. Constant means doesn't change. And it's this number, 6.67 times 10 to the minus 11th. And the units are newtons, meters squared. Newtons is a force unit, if you remember. Meters is a distance unit, over kilograms squared. And the reason these units are so strange is because it's needed in order to cancel out things in the equation. When we see a problem shortly, we'll see how that equation is used. Let's go right to a problem here. If we go right to a problem and we ask, what is the force of gravity between a 70-kilogram man and the Earth? And the reason we chose a 70-kilogram man was we would find that type of person in a high school class. So what we need to do is we need a little drawing never hurts. So here's an Earth, if you will, or a planet, and there's a person standing on the planet, and we are going to find the force of gravity between them, that person and the planet. And so the first thing we always do is we write down the formula. We never start a problem without writing down the formula first. So we've written down the formula, and we're now going to put the numbers in the formula. So here we go, and this should go pretty fast. So the force of gravity, we need big G, which is 6.67 times 10 to the minus 11th Newton meter squared over kilogram squared. That number will be given to you anytime we have a test. It's not a number we memorize. We can look that up. Then we need the mass of the two objects. Well, obviously the mass of one of the objects is 70 kilograms. The mass of the other object is the planet Earth. So we have a person and the planet Earth. Well, the planet Earth is a specific mass, and that can be looked up. And again, it's a number that would normally be given to you because people don't memorize these numbers. The mass of the Earth is 5.98 times 10 to the 24th kilograms. And in future lectures, I can explain to you how we actually determined the mass of the Earth. Now, we need to divide by the distance. And one would say, well, you're standing around the Earth, there's no distance between you. However, distances for objects are, since the objects are not pinpoints, have to be measured from one place to another. They're always measured from the center of the object to the center of the object. Well, in this case, we would need to know the radius of the Earth. And the radius of the Earth is a well-known established fact. And it does change depending upon where you're standing on the Earth. But overall, the average radius of the Earth is 6.37 times 10 to the 6th meters. And of course, the formula says that's got to be squared. Now you'd say, well, what about measuring the height to the middle of the man? And that's a good question. If you were to add on an extra 90 centimeters from the feet of the person to the middle of their person, you would add 90 centimeters to this number 6.37 times 10 to the 6 meters, which is 6 million some odd meters. I don't think that's going to make a big enough difference. And even if you're like 3 feet off the ground, it's going to be roughly the same number. It's not till you get a significant digit or distance off the ground that it begins to make a difference. So in your calculator, we would now punch in all of these numbers, and we can't forget to square the number on the bottom. It's a lot of number crunching in the calculator, and it's good if you know how to use the exponential parts in your calculator. So I would put in 6.67. I would not type in times 10 to the minus 11. I'd put the EE button and then put negative 11. That would give us the same thing as times 10 to the multiplied by 70, multiplied by 5.98, EE to the 24th, again, or that means times 10 to the 24th, divided by 6.37, EE to the 6th, then squared. And after you press equals, you get a force of 688 newtons. And so the force of gravity on this person is 688 newtons. That is the force of gravity that the person is pulling down, or the Earth is pulling down on the man. If I were to change this problem around and I say, well, how much force is the person pulling on the Earth, we would find out that it is the exact same amount. You see, if the Earth pulls down on you, you pull on the Earth. That's Newton's third law, action and reaction. It happens to be the exact same amount of force. Now, since the Earth is so large, you're not going to move the Earth very much. If the Earth is pulling it on you, it will move you toward the Earth, but you will have a hard time moving the Earth. I might also add that this answer could have been gotten by another method. Newton's law is F equals ma. We learned that a few lectures ago when we were talking about Newton's laws of motion. And the mass of this person is 70 kilograms, and the acceleration due to Earth, gravity on Earth is 9.81. And that would, I'm sorry, I should put the units here. It's meters per second squared. And kilogram meters per second squared is the unit for Newton. And if we do this math, we also get 688. This method, F equals ma, is a short form that can be used, but only if you're on the surface of the Earth. If I could take a time out here and just backtrack a moment to the previous part of the problem. I didn't, at this point, tell you about the units. The kilograms of the two masses cancel with the kilograms squared. And the meter squared on the bottom cancels the meter squared on the top. And the unit left is newtons, and that is the correct force unit in the metric system. And so I just wanted to make sure you understood that newtons was the proper unit. Let's move on to another problem. In this particular problem, we're the force of gravity between the moon and the Earth. And I try to use real numbers, and these are real numbers. It's asking for the distance between the moon and the Earth. What is the distance between the moon and the Earth? In this, they've given you the force, and they've given you the mass of the Earth and the mass of the moon. And they're written here, if you notice, it says m sub e and m sub m. Well, before you go and put numbers in a formula, let me show you something you need to do first. First of all, we write down the formula. F equals big G mass 1 mass 2 over d squared. Now, we're trying to determine the distance between the moon and the Earth. So our job is to find this number right here, the distance. What we should do before we put the numbers in is we should rearrange the formula. And the reason we want to rearrange the formula is because we don't want to have to keep writing the numbers several times when we rearrange it. So to rearrange this formula, for those people who are good at Algebra 1, and you should be, we're going to multiply both sides by d squared. But at the same time, we're going to divide both sides by f. So our new formula is going to become d squared equals g mass 1 mass 2 over f. Now, in the end, we're going to need the square root, which we will do. So let's now put the numbers in. And I'll do this over on the right where we have some space, and we also will be able to see the numbers. So d squared equals g, which is 6.67 times 10 to the minus 11. And it comes in newtons, meters squared over kilograms squared. And the two masses they've given us is 5.98 times 10 to the 24th. That's the mass of the Earth, and that's in kilograms. And the mass of the moon, which is 7.35 times 10 to the 22nd kilograms. The moon is got 2 less zeros, 10 to the 22nd. It's about 1/100th the size of the planet Earth. Divided by, and now notice my formula now says forces on the bottom, so that'd be 1.99 times 10 to the 20th newtons. Now it looks like a bunch of number crunching, but before we do the number crunching, let me check out my units. Kilograms squared are going to cancel with those 2 kilograms. This newton is going to cancel with that newton. And the unit left is meters squared. However, we're going to have to square root this. So you can see that's going to work out nicely. So we do this work. We're going to go 6.67 in our calculator. And I encourage you to use the EE button, not the times 10 to the raised to the negative 11. That takes a lot of time. Times 5.98 EE to the 24th times 7.35 EE to the 22nd divided by 1.99 EE to the 20th. And then you got to remember at the end, after you press equals, you got to square root this. The correct answer, after you square root it, is 3.83, almost 3.84. Let's round it up. 3.84 times 10 to the 8th meters. To give you an idea, that's roughly about 240,000 miles. Actually, if you do this, it's 238,000 miles. And that is the correct distance to the moon. So now if you look, we've used our formula now twice. We've used it to find force. We've used it to find distance. We're now going to use this formula one last time. And it says 2 identical books are 40 centimeters apart on a table having a force of gravity between them. What is the mass of one book? Let's go right away. F equals big G, mass 1, mass 2, over d squared. In this problem, we're looking for the mass of a book, but they're identical books. So what I'm going to do is a little bit of algebra 1. For those people who know this, I'm going to multiply up by d squared. I'm going to divide down by g. So my new formula says F times d squared over g equals m1, m2. Now they're identical books. And usually I have this argument with my students. Is m1 times m2, is that 2m or is it m squared? Well, if you think about this, m times m is m squared. M plus m is 2m. So we're going to deal with m squared. So the new equation looks like this. M squared equals force times distance squared over g. And I encourage you to rearrange the formula first. It makes putting in the work a lot easier. So here we go. M squared equals the force. They told us the force was 1.1 times 10 to the minus 8th newtons. There isn't a lot of force between 2 books that are sitting on a table. The distance between them, now it says 40 centimeters. However, before I put in that, let me come back and put in big G. Big G is 6.67 times 10 to the minus 11th Newton meters squared over kilograms squared. Since big G is done in meters squared, in order to get our units to cancel, we're going to have to do distances in meters. And so that'd be 0.40 meters squared. Now, if you look for units, the meters are going to, or the newtons are going to cancel, the meters squared are going to cancel, and we're going to have kilograms squared on the bottom, which is going to flip over, and we're going to square root it, and it's going to come out to be kilograms, which is exactly what we want. So in our calculator, we go 1.1 raised to the minus, or e to the minus 8th times 0.40 squared divided by our big G number, which we're now getting used to because we used it a lot. And don't forget to square root at the end. A lot of people forget to square root at the end. And I have a mass here of 5.14 kilograms. So the mass of each book is about 5 kilograms. That's kind of a heavy book. All right. If you look at how we've done these problems in today's work, what we've done is we first discovered what gravity was and what the formula is. And then we did a problem where we had to solve for the force. We did a problem where we had to solve for the distance. And we did a problem where we had to solve for the mass. And so those give you three good ways to solve for things. I'd like now just to take a moment out and talk about Newton's law of gravity. Newton was the one who came up with this law. And there's quite a bit of, in my class, you'd get quite a bit of discussion about who Newton was and how it was that he came about this. But back around 1900, the turn of the last century, Einstein came up and said, there's got to be a better explanation for gravity. You see, how does the moon know that the Earth is pulling on it? Or how does anybody know that the Earth is pulling on it? And if all of a sudden the sun or a planet were stopped pulling or disappeared, how would the moon or how would the communication happen between the two objects to know, hey, I'm not pulling on you anymore? The moon is kept in orbit because the Earth is pulling on it. If the Earth all of a sudden disappeared, how would the moon know not to do this? And there are some conflicts that are much more mathematical to understand. But this theory, although Newton's law of gravity is a very good law, and it works, and it helps us send spacecraft to various planets and things, and we use it all the time, it is not the complete theory of gravity. Einstein said, no, it can't be one thing pulling on another. And so Einstein redefined gravity and said, no, gravity is a warping of the space-time fabric. Now, let me see if I can give you a little explanation of this. If you were to take a bed sheet or something like this and put a large mass in it, like a bowling ball, it would depress that bed sheet or any type of fabric, if you will, and it would cause a depression. So here's a picture of a fabric with the Earth sitting on it. Now, this is a two-dimensional picture where in Einstein's theory, we have to think in three dimensions, and it's much more complicated to think about. But Einstein said, listen, if you were to have a mass travel by here, a mass traveling by here would bend according to the fabric of space. And I'm not sure that pen showed up very well. Let me see if this pen would show up a little better. It would bend according to the fabric of space. So if that Earth was not there on that fabric, the object would just go straight. Well, Einstein said, really, gravity is a curvature of space-time. And the bigger the mass is, the more it curves the space fabric around it. And so therefore, for instance, if we had a large mass like the sun, when the Earth falls within its realm, it would just fall and circle around it, as if you rolled a marble and it would just go in a circle. If we took the sun out of this and the fabric were to flatten out, the Earth would just go in a straight line. This is a much more complicated theory it's his general theory of relativity, and it actually explains gravity better mathematically than Newton's method. We still use Newton's method. It's still used, like I said, to put rockets in orbit and things. However, we now have come to the understanding that gravity is actually not one mass tugging on another. It's really a bending of the space-time continuum. And that requires much more discussion, and that will have to happen at another time.